In 1630, Italian scientist Galileo went to the Leaning Tower of Pisa. In his hand, he had a 1-pound ball and a 10-pound ball. He dropped these balls at the same time from a great height and learned, to the amazement of the people below, the balls fell at the same rate.
400 years ago, or so the story goes, Galileo Galilei started dropping things off the Leaning Tower of Pisa. Cannonballs, musket balls, gold, silver, and wood. He might have expected the heavier objects to fall faster. Not so. They all hit the ground at the same time, and so he made a big discovery. Gravity accelerates all objects at the same rate, regardless of their mass or composition. Nowadays, this is called the universality of freefall, or the equivalence principle, and it is a cornerstone of modern physics. In particular, Einstein crafted his theory of gravity, in other words, the general theory of relativity, assuming the equivalence principle to be true. But what if it's wrong? Some modern theories actually suggest that the acceleration of gravity does depend on the material composition of the object in a very subtle way, says Jim Williams, a physicist at NASA's Jet Propulsion Laboratory. If so, the theory of relativity would need rewriting. There would be a revolution in physics. A group of NASA-supported researchers are going to test the equivalence principle by shooting laser beams at the moon. Lunar laser ranging is one of the most important tools we have for searching for flaws in Einstein's general theory of relativity, says Slava Turishev, a research scientist at NASA's Jet Propulsion Laboratory, who works with Jim Williams and others on the project. Their experiment is possible because, more than 30 years ago, Apollo astronauts put mirrors on the moon, small arrays of retroreflectors that can intercept laser beams from Earth and bounce them straight back. Using lasers and mirrors, researchers can ping the moon and precisely monitor its motion around Earth. It's a modern version of the Leaning Tower of Pisa experiment. Instead of dropping balls to the ground, the researchers will watch the Earth and Moon drop toward the Sun. Like musket balls and cannonballs dropped from the tower, the Earth and Moon are made of a different mix of elements, and they have different masses. Are they accelerated toward the Sun at the same rate? If yes, the equivalence principle holds. If not, let the revolution begin. A violation of the equivalence principle would reveal itself as a skewing of the Moon's orbit either toward or away from the Sun. Using masses as large as the Earth and Moon, we may be able to show this subtle effect, if it exists, notes Williams. Scientists have been pinging the Moon since the Apollo days. So far, Einstein's theory of gravity and the equivalence principle has held up to a precision of a few parts in 10 to the 13. But that's not good enough to test all the theories vying to overthrow Einstein. Current lunar laser ranging can measure the distance to the Moon, roughly 385,000 kilometers, with an error of about 1.7 centimeters. Beginning this fall, a new facility funded by NASA and the National Science Foundation will boost this accuracy tenfold to within only 1 to 2 millimeters. This jump in accuracy will mean that scientists can detect deviations from Einstein's theory 10 times smaller than currently possible, which may be sensitive enough to find the first evidence of flaws. To achieve that accuracy, the facility, called the Apache Point Observatory Lunar Laser Ranging Operation, or APOLLO, must time the laser pulse's round trip to the Moon within a few picoseconds, or just a trillionth of a second. The speed of light is known. It's about 300,000 kilometers per second. So measuring the time of flight for the laser pulse tells scientists the distance between the Apollo telescope and the mirror sitting on the surface of the Moon. How does Apollo's design achieve this tenfold improvement? First of all, it uses a larger telescope than the older facility at the McDonald Observatory in Texas, 3.5 meters versus 0.7 meters. The larger mirror lets the Apollo facility catch more of the photons of light returning from the Moon, explains Tom Murphy, a professor at the University of California, San Diego, and the mastermind behind the design of Apollo. The smaller telescope catches on average only one returning photon for every 100 outgoing laser pulses. Each pulse contains more than 10 to the 17 photons. The Apollo telescope will catch about 5 photons from each pulse, which greatly improves the statistical strength of the results. Several potential disturbances had to be reckoned with. Earth's atmosphere, for one, can distort the path of the pulse of laser light in the same way that it causes starlight to twinkle and shimmer. And tiny tectonic motions of the ground beneath the Apollo Observatory, typically a few centimeters per year, could skew the long-term results. So the project leaders chose a mountaintop near White Sands, New Mexico, that enjoys a particularly calm overhead atmosphere and ground that is relatively stable. In addition, they are installing a superconducting gravimeter and precision GPS sensor alongside the observatory to detect slow ground movements, and an array of precision barometers will map out the state of the atmosphere. Williams and Turyshev have recently received a grant from NASA's Office of Biological and Physical Research to improve JPL's lunar laser ranging analysis software by an order of magnitude to match the capability of the New Mexico site. It will be necessary to deal with many small effects at the millimeter level, notes Turyshev. Through careful accounting of such small effects, the universality of freefall could fall. Many physicists would welcome the news. They've been puzzled for years by a curious incompatibility between the theory of general relativity and quantum mechanics. The two theories, so successful in their own realms, are like different languages describing the universe in fundamentally different ways. Read the Science at NASA story Evicting Einstein to learn more about this. Finding a flaw in the underpinnings of relativity could lead to a new theory of everything, finally combining quantum physics and gravity in one harmonious framework. From Pisa, Italy, to the Moon, to White Sands, New Mexico, this is a far-flung experiment spanning hundreds of years and hundreds of thousands of miles. Soon, perhaps, we'll have the answers. This story was written by Tony Phillips and Patrick Berry and read by Tony Phillips. It's presented by Science at NASA. To find more Science at NASA stories on the Internet, please visit science.nasa.gov.